So we sharing the link. So last class we talked about current, electricity. We talked about electrostatics and electric field. So we talked about electrostatics and electric field. We dealt with capacitors, and to some extent we summarized buying electrical energy and power. And talked about fuse rating and some things. But if you know those parts well, that covers all your level of exams aside one school. So, but if you are writing any school aside OAU, OAU2 is basically your OAU physics is normal level. It's always low level. It might just be using some percentages for you, some units and all of those things. It's only OAU chemistry that is usually an advanced level. But the physics, if you have written it before or you have seen the past question, you will see that the physics is always normal level. And it is on these slides too that they just test you. It's still normal level, but they just want to check one or two things when they are setting questions for you on lenses, especially. So, but there's nothing too difficult. But for every other school, so far so good. If you can just practice questions based on all the things we have talked about, you can write any of the exams, be it WAEC, NECO, JAM, post-UTM. So today, I'll just briefly go through light. So I've talked about reflection of light at plane and curved surfaces. That's in mirrors. Then I'll talk about refraction of light. So we talked about refraction in rectangular prism, triangular prism, and refraction through lenses. Because we want to try and end the class as early as possible, due to some arrangements we are making, our class might end around 1 today and not 4. That's early enough, I think. So let's start. And I think the Muslims too, we have to go to the mosque. So let's start with, can we share the links now on our pages and groups and everywhere so that people can join? So if you are online, you can also share the links with people so that they can join the class live and you learn from the comforts of the
So we can carry the link now.
Share it on 4 days.
I'll share it everywhere.
So we are waiting for the links to be shared so that we can continue our classes. So first to start with will be lights. No symbol.
Just remember to them to me. Have you seen the umbrella student to you? Yes, ma'am.
Good morning, sir. How are you, sir? Hello, no, you don't need them over. Sorry, I lied. So, if JP has time, you can please send maybe
Change
so that you can just check together. So that will not need the extra. When is class starting? And it should just show you, that's why, so that you can just check out. So, just to quickly show so that we check what is needed. So, let's start with light energy before we move on to the rest. So, the first thing you need to know is what is light itself. All of you can see lights in those places. And God said, let there be lights. And there was light. So, but that light, because you can see it, we call it visible light. So light energy, it's an energy that radiates from a source, that comes out from a source. And light energy is a part of the electromagnetic spectrum. You have done introduction to wave, Abby. So you know the difference between electromagnetic wave and mechanical waves, Abby. So your electromagnetic waves, like your Riemann G, where you talked about the radio waves, Abby, infrared waves, microwaves, which other one? Sorry, it's radio wave X, then Riemann G. So talking about radio waves, microwaves, infrared waves, visible light, ultraviolet, X-rays, and gamma rays. So this part of these waves is what we are trying to study. So we call it the visible light. So visible light is a form of energy. And you remember, this visible light that we are talking about, it also has different categories from rainbow. So this visible light is made up of 7 parts that we call the Roy beam. That is your red color, your orange color, your yellow color, your green color, your blue color, your indigo, and your violet. So these are called the visible lights. Those are the lights that the wavelengths of the light your eye can perceive. But when they all come together, they come as white lights. So you are seeing white light most times. But when that white light is dispersed, you can see different colors. And that's what happens when rain falls and you see rainbow. But that's not what we want to study today. So we are focusing on light itself because light has a lot of application. Without light, you cannot see me. Fine, you can see me. I'm the light of the world. But without light, you cannot see your faces. We cannot see you from the table. We cannot see everything that is in front of you, both the books and all. So light is an important aspect. Without light, you cannot even look at yourself in the mirror and say, I'm beautiful. It's not possible. So from what you have, light is very important. So light is a part of electromagnetic wave that we call visible light. Is that taken? Now, one thing you need to know from what you have studied about electromagnetic waves, frequency always increase this way, Abby. So that means that gamma ray has the what? Highest frequency. From what you have here too, frequency, you know, it's going like this. So if you are picking a part of visible light out, frequency will also increase from red to violet. Is that taken? So that means that this one will have the highest frequency. Now, all this electromagnetic wave, I hope you still know that they move at the speed of light. 3 times 10 raised by 8 meters per second. That speed. So sometimes they can ask you some questions that they will not give you that speed of light. They might say calculate the wavelength of light, which you are going to use V is equal to F lambda, and they will not give you V. And they are talking about light. The moment you hear the word light, that means you are going to use the speed, this. But if they say that calculate the wavelength of sound, that means that what will be your speed? Yeah? You people have forgotten. The moment they say calculate the wavelength of sound and they give you the frequency and they didn't give you the speed, just know your speed is either 330 or 340 meters per second. All of these are, you have to know them. So this is called the speed of light. This is called the speed of sound. And you need to wait naturally. Sometimes I test that. And even in my exam that I wrote recently, they didn't give speed and all of those things. And thank God for grace. So yesterday I felt I was going to read everything that had to do with the exam. But the issue of pregnancy and this did not allow me to have time to read. But I still entered the exam and thank God for grace. I still know, at least I know maybe 55 out of the 60. Out of the 60 questions. Like how would I do the remaining 5? But thank God for grace. I will say more than that. I shall do the remaining 5. So because I was unable to do tests. And when I did that course in Wales, I actually had 93 over 100. I was like, Because here now, I now have me. But I was just scared because I didn't read anything from the beginning of this to that yesterday. But since it was chemistry, I felt God did. So God did. So it's a testimony. Continue to read every day, not to the day of the exam. You don't know what tomorrow holds. I have exam tomorrow, I have exam tomorrow, and you are not reading. I wish you know, it's still far, it's still far. When it's near, God will not allow you to be sick. Those are the prayers. So what we call the visible light is Roy beam. So don't forget that frequency increase this way, and wavelengths increase this way. So this is how wavelengths increase. So this one has the highest wavelength. Wavelengths always range. You might have seen that they will write that the wavelength is always from 400 nanometer to 700 nanometer. I hope you know 700 is greater than 400. You can go back to primary school if you don't know. Now, from what we have here, they always say that the wavelengths range from 400 to 700. It does not mean that this is the one with 700. But you know they can say wavelength range from 700 to 400. So a statement is you go from smaller to the highest. But this one has the highest. So they can ask you, especially when you use students, they can ask you. So this one is around the 700 nanometer. Why this one is around the 400 nanometer? She gets. So wavelength decrease as you are going here. Now, if you're talking in terms of energy increase, Abby, as you move from here to here because frequency is increasing. You remember, H is E is equal to what? HF. I'm talking about some basic properties that we need to have known from studying electromagnetic wave. That's not the purpose of our class, but just giving you some background knowledge again. E is equal to HF. If frequency is increasing, energy will increase because this is called a Planck constant. It's a constant. So as frequency is increasing, as you are going this way, that means gamma ray will have the highest form of what? Energy. So you need to just know those stories. So the next, so that one is called natural. So any source that can give it, so that one is called natural. So any source that can give its own light is said to be luminous. Is that taken? I hope you're writing and you are listening. Yes. So we now have two types of luminous sources. We have what we call natural luminous sources. And we have who is sun. Abby? Which other example? Abby? Which other example? Glowing worm. Glowing worm, Abby? Sun, star, which other one? So your glowing worm, your fireflies, Abby? Have you seen fireflies before? So they give their own, most of your candles. Candle cannot warm it, Abby. So that is what we call artificial source of light. Is that taken? Non-luminous sources. We see them based on light they reflect. All your faces are non-luminous. Even if you say that you are radiant, well, it's biblical. We look unto him and we are radiant, and our faces are not ashamed. Preach on, Pastor. Even if you say you are radiant, you are still reflecting radiation of light, or probably you have used vegetable oil on your face. So now, non-luminous sources, all they do is that if you can see them like this board now, you are only able to see because it is reflecting light. So they reflect light. So they do not produce light of their own, but they reflect light. So as the light is shining on my face, I'm reflecting it, and you can see me brightly. So that is what we call non-luminous sources. So most of the things you see around you, they are non-luminous sources. You're walking without knowing what is going on. Only yellow people like me can you see. So now, from what we have, when you have talked about sources, there is a way light is transmitted. For light to move, light travels out from a source, and that part that light takes, we call it the ray of light. Light moving from one to another place, so we call it ray. So in transmission, you need to know the difference between what we call ray and what we call beam. So ray is simply defined as the path taken by light. That means the path that the light follows. Where you shine lights, there's a path it follows. So that path taken by the light is called the ray. Now, collection of rays is what we call beams. I hope you are following. So we have what we call beam of light, collection of rays. So light is seen to travel like this along a straight line. Then when lights come together, then we call it collection. So when rays come together, we call it beam. And that's what you have everywhere. So these lights now can disperse. You have seen different touch lights before. Some can just go straight in a parallel manner. Sunlight comes as a parallel ray too. So when you're talking about collection of rays, I think that light is seriously important. So we have different types of beam of light. We have parallel beam, we have divergent beam, and we have convergent beam. So we have divergent and convergent. So when you're talking about the beams of light, when you have several rays that are moving along the same line and are equally spaced, then you say that is a parallel beam of light. When you have beam of light that they radiate from a source, a common source, and they move out, they spread out. The English is there, diverge. Diverge means spread out. Converge means come together. So there are different ways in which light come together. So converge means that all of them are coming from a source and they are meeting together at a point. So without wasting time. So that is what we call convergent rays. So you can see I have several rays now. So several rays emanating from a common source and spreading out. Then we call them divergent rays. Then the ones that come together to a particular point, we call them convergent rays. We'll be using these terms as we are moving on. There's still what we call incidence ray, normal ray, everything is a ray. Just know what ray means. So now, talking about the paths in which light takes, then we have what we call rectilinear propagation of light. Rectilinear propagation of light. From the word rectilinear, you have studied rectilinear motion before. So rectilinear propagation of light is talking about ability of light to travel along a straight line. So light traveling along a straight line is what we call rectilinear. So light traveling along a straight line is called what? Rectilinear propagation of light. So now let's move on from there. Now when you're talking about rectilinear propagation of light, light has different applications. I want to believe you are following what I'm saying here. So don't forget, for your non-luminous example, you have a moon, because they can ask you. Moon is non-luminous, so moon only shows you light it reflects. So moon is a common example that they can ask you. Is that taken? It does not give its own light, but moon will only give light based on the light it has taken from the sun and all of those things. So we have moon, all your faces, I've said a lot of examples, but don't forget moon, it's very important. So now, we have I said, let's look at there are different materials that light pass through. Now, if light falls, the person wants to see the light through. If I'm behind this board now, and light is shining on the board, you cannot see me. Why can you not see me? Because this board is opaque. Abby? So we have different materials based on if you shine lights on them. I think there was a question you asked about that last year. So you have different materials. You have what we call a translucent material. We have what we call a transparent material, Abby. Those are just basic English. And we have what we call an opaque material. Please remind me, everybody, is moon artificial or non-luminous? Non-luminous. Okay. Because my brain is coming back to say that I made a mistake there. So let's look at it. For materials, we have translucent, transparent, and opaque. Those are different materials we have. And from the word transparent or translucent, translucent means, starting from here, this one means that light can easily pass through. Light passes through easily and can be seen easily. So if you look at the transparent objects, you will see through the transparent objects. Abi, I hope following. So if you look at the transparent object, you can look through that transparent object. So if you say that you want to be transparent in all your dealings, that means that everything you do, you are not lying. People can see it clearly that you are doing it. So you justify it with everything. It's not just by mouth. As you are doing it, people can tell for real that you are transparent enough by telling them what you have done and everything that you are still doing. So transparent. So if you see a glass that is very, very clean, even water that is very, very clean, you know you can see through the water. So all of those things are said to be transparent. The ones that you can only see partially, you see partially, and light also pass through partially. Light pass partially. Then those ones are said to be translucent. Is that taken? So now, if you have a glass that is frozen, if you have a clean glass, if they tell you that it's a very clean glass, it will be transparent. But if you have a frozen glass, you know what that means? It has been iced. And when you bring the glass out, it has a lot of vapor. When you look, you can't really see clearly, but at least you see to some extent. Then that is an example. So your frozen glass is an example of even a paper that has been stained with oil. So a paper that has been stained with oil can also be translucent. Then we have your clear glass, clear water, and all of those stuffs. So we have them to be transparent. Opaque objects are objects you cannot even see through. Cannot see through. Light does not pass through, and you cannot see through. They don't allow light to pass. They block light. That is what we call an opaque object. So without wasting time, your light, when light is sent out, light can be either transmitted. That means that if the light strikes a material, the light might go through the material and pass on, maybe through a glass. The light will transfer from one region to another region, so it can be transmitted. Then when light strikes a material, the light can also be absorbed. So when light strikes now, this thing absorbs the light, or it can also be reflected. So most times when we are talking about light can either be reflected, transmitted, or absorbed when it strikes a material. So some part of it is usually absorbed, some part is usually transmitted, and some part is usually reflected. So we need to know this about transmission of light, just for the way. Now, when you know all these different materials, we now have what we call an application of rectilinear propagation. This is just an introductory class. We're going to go to reflection. It's something that you all should have known before. But let's say you are just entering SS1. Everything I've said, you should try and know them and work on this so far. So now, when you're talking about applications, we have what we call rectilinear propagation. What did I call rectilinear propagation again? Ability of light to travel along a straight line. So this rectilinear propagation has applications. So let me summarize the applications. So the applications are in three forms for this class. We have shadow, formation of shadow. If you can see the board now, you will see that as I'm blocking the path of light, you can see the shadow of my hand on the board. But if my hand is not there, there will be no shadow. All because my hand is an opaque object. So when I block the path of light, the light is not able to go through my hand and get here. And that's why you are seeing shadow. So if light has not been traveling along the straight line, I won't block it. You know that by the time the light gets here and it sees that there is no way, we'll curve around and go to the back. But because it's a straight line, so if something is coming along the straight line and you block it, that's all. The thing cannot curve around and all. So that is what is happening to light that is able to give us shadow. So the ability of the light to travel along a straight line has an application in the formation of shadow, in the formation of eclipse, and in the formation of, in working of Pinhole camera. So let's summarize how these three happen. So when you're talking about shadow, Shadow is just blocking a part of light. So when you take an opaque object, I will leave the screen for those of you that are not seeing. An opaque object is an object that light cannot pass through. So just imagine this is an opaque object. Now, let's say I'm shining light on this opaque object. So this is candle. Now, I have a screen. So this is an opaque object. This is my source of light. Are you following? So now, this is my screen. Naturally, when the light travels from this candle, it should touch the screen. But because I'm placing something along the path, something will happen. Now, the light that is supposed to travel along the straight line, go this way, evade the opaque object. The light travels this way, evade the opaque object. The light can decide to travel this way. So at the end of the day, what will you notice? This should have been through here. So what will you notice? Now, this guy's shadow, just like the same way, you know, if I put my hand between the light and the screen, what will I see on the screen? Shadow. Abi? So it's the same thing. So if this object now is blocking the path of light, shadow will be seen. So this place will be dark. Do you get that? All because the opaque object is blocking the path of the light. So as I'm blocking it, let's say the body is the screen now. My hand is the opaque object. So I put it in between. Now notice something. Because it's important, they can use that to ask you a question. Look at this light. If I block it, you can see shadow. But the shadow is not that dark. It's bright. All because the source of light is extensive. The source of light is more. So the shadow is not that dark. But if the source of light is very small, have you ever seen maybe a candle is lighted and you try to block that candle? You see how dark the shadow will be on the board. So if the source of light is, so you need to know this. If the source of light is a point source, we have two types of sources. This light is serving a serious energetic effect in my phone and in my room. So if the source of light is just a point source, that means it's tiny. The shadow will be very, very dark. So you're going to have a dark, obvious shadow. Do you get that? But if the source of light is extensive, that means that the source of light spreads out more, then the shadow will be bright. You will still have shadow, but it's going to be a bright shadow. So let's leave that part. Now let's move on to eclipse. Is that taken? I hope you are following. Please, so I'm not too fast. I might not just give you notes, that's the thing. But I'm not too fast. So now, when you talk about eclipse is, we have heard about eclipse before, but quickly, eclipse is just, we have the sun shining its lights. Now you remember Earth is non-luminous. If there is no sun, will you be able to see? We won't see. It's because when sun comes out, that's when everybody can go on their day-to-day activities. But by the time sun leaves, everywhere will be so dark. And that's why we start producing artificial light, so that we can also see. But God has said there should be difference between day and night. God knows what he's doing. Because if God knows that if the day is just full of light, everybody will not sleep. Especially some of you keep walking up and down. Hello? Hey now, you should have JP did not tell you. Why don't you get class? Class suppose dey hospital, na me give birth. And shey dem don tell you say na from one born you dey comot. Man dey look at her face. I think I still dey there. Even if I dey there, she dey there. Alpha. JP for don't tell you all these things now, because I did live stream the class. Even if I did keep these ones with online events, I'll call you if I don't finish. I dey come UK soon. So now the earth is non-luminous. The moon is also non-luminous. Now, if this moon, we said moon is non-luminous. Now, the earth is rotating the sun, the moon is rotating the earth, and all of those things. So it's just like this guy is going like this, and this guy is going like this. And at the end of the day, there's a time that this guy might be between the sun and the earth, and there's a time that this guy might be, if he gets here and he gets here, the earth will be between, so now the light coming from the sun, the earth can block it so that the moon will not get the light. Do you get that? Just like shadow. If the moon is here, the light coming from the sun, the moon might block it so that the earth will not get that light. Do you get that? Then when this thing happens, we call it what? An eclipse. So if the earth blocks the light from getting to the moon, we call it lunar eclipse. So eclipse is just talking about those blockages that I just explained. So you can read more about how they are blocking or not. The most important thing is for you to understand the types of eclipse we have. So for the first one, we have what we call lunar eclipse. And that lunar eclipse, just remember lucerne. Lunar. This means lunar eclipse happens when the earth is between the sun and the moon. Is that taken? Because it's easier to pay more for that. So when the earth is between the sun and the moon, you have lunar eclipse. So I will talk about the next one, but let's quickly look lunar eclipse. So you have the sun and you have the earth. Then you have the moon. So now when ray of light comes from the earth, from the sun, then you have this. So sorry people on this side. So when this is the sun, this is the earth, this is the moon. So when ray of light comes from the sun through the earth to the moon, because the earth is an opaque object, so light cannot pass through. So the lights that are coming will only find their ways, those ones that can pass through. At the end of the day, this part of that is blocked by the earth that light will not get through will be very, very dark. So that I won't have time to start shading it, but just know that this part is totally dark. And that part that is dark is called umbra. It's called umbra. So that part that is dark, even you are not there, we have been going there. So that part that is dark is called the umbra. But light, as the light is coming, a part of this place can still. So if someone is around here, and someone is around here, and someone is around here, A, B, and C. Someone that is in B will not see light at all. The person will see what we call total darkness. So that is what umbra means. Total darkness. Are you following? So, but people in A and C, they can still see light a bit. Then we say they see partial darkness. So people in A and C, they will see what we call penumbra. Penumbra, which is called partial darkness. So penumbra region is also called the gray region. Gray region, just a place that you can see partial light. So it's your gray region. Are you following? So that is called the penumbra. Is that taking? If there's anything that is not clear, you can quickly let me know so I explain it further to you if you don't understand this. So I said you have lucerne, Abi. What does lucerne mean? Lunar eclipse occurs when the earth is between the sun and the moon. So we call it lunar eclipse. So the second type of eclipse is called solar eclipse. Are you through with this? So let's move on to solar eclipse when you are through with that. We are still on applications of rectilinear propagation. So when you are through with that, so let's move on to the next thing. It's not so hard. If you can just read all those summary that I've said and practice questions, you don't have much time. where they will ask you questions very well, we have not even gotten there. And the technicality of solving questions are important. So please, let's move on. So let's move on. So the second part that we have, what is complementarity? Now. So the second part is what we call the solar eclipse. So this one I will take something together, but before that let me just first take the first thing. So if you already know that it is when the earth is between sun and the moon that we call lunar, then what do you think solar will be? So you can remember when the moon is between the earth and the sun, then we have what we call solar eclipse. But if you remember that, you automatically remember this one. So that one is when the earth is between the sun and the moon. So now, let's say this is our sun and this is our moon. I hope you know that moon is smaller than earth and earth is smaller than moon. Which one? Now, this is your moon, this is your sun, this is your earth. Now, some ray of light coming from the sun might not get to the earth when they strike the moon. So at the end of the day, we have our region. So let's say this is the A, this is the B, and this is the C. What's the A region called? Umbra. What's your B region? And the C region. So you already know that. So let's now see an exception to this. Sometimes this guy might be very close to the earth. That's what you call it in geography, hypogea and epicenter. Now, when this guy is very close to the earth, or this guy is very close to the sun, something happens. So let's say this is the sun now. Then the moon is kind of close. I don't want to waste spaces. The moon is kind of close to the sun and the earth. As the ray of light is coming from the sun, as it passes through the moon, coming from here, you notice something that never happened before. What did you notice here? This ray, look at this ray coming and look at this ray coming. Where did they meet? Here on earth, Abi. But this ray coming and this ray coming, before they get to the earth, they already intersect, Abi. They are now forming something like a cone. Do you get that? Yes. So now, this region will now be your dark region. It's no longer everything now. So this part is now what we call your umbra. But this part that follows it, we call it atumbra. Atumbra. Just like antiumbra. People that are here can still see light, but they will not see the light like shining. They will see it like a ring of light. So people here are said to see a ring of light at that atumbra region. I will write something about it. Then this place still remains your penumbra. So how do you form atumbra? We already know about umbra and penumbra, so let's talk about atumbra. You form atumbra when the rays from sun intersect intersects before getting to the earth. So when the ray of light coming from the sun intersects before getting to the earth, you form an atumbral region. So atumbral region is a region, so it is a region where a ring of light is seen, and it is formed beyond the vertex of the cone. So the atumbral region, it's a region beyond, it's a region where a ring of light is formed, because of those watching, in case they are not seeing, so I'm dictating it. A region where a ring of light is formed, and it is formed before getting to the earth. So there will be an intercept. So this part is called the vertex. That top, you know, those of you that know about cone, your cone, Abby, this part is called your vertex, Abby, the vertex of a cone. So beyond that vertex, that's where you have your atumbra. Beyond that vertex. So beyond this place now, I have atumbra. Then that is the thing. So what do you see around the atumbra? A ring of light. What do you see at the umbra? What do you see at umbra? Nothing. That's total darkness. But at the penumbra, you see what? A partial light. But at the atumbra, you see what? A ring of light. Is that taken? So that's that about that. So for a Pinhole camera, when you are through with that, oh yeah, you are right. So let's end it with a Pinhole camera so that we can go to reflection of light at plane and curved surfaces. So this is the introduction to the class. I'm just trying to wait for you to write. Can we move on? Yeah, let's move fast. You can put the camera on it so that they can see the board in case they are renting. Are you true? People are saying they have a question. If you have a question, you can post your question. So can we move on now? So let's look at Pinhole camera. Just a form of light, that's a form of camera that's, you know, those days when there were not much of things that could be used as proper camera. So we use what we call a Pinhole camera, and this Pinhole camera works on the ability of light to travel along a straight line to capture images. So now a Pinhole camera is just made of something like a box with a very tiny hole at the front. That's why I call it a Pinhole camera. Then the part of this part of the Pinhole camera is the screen, where the image is formed, where the image of the object is formed. So you have an object, sorry. So let's say this is an object that is placed in front of a Pinhole camera. Let me make it to be as if this is the ground level. So an object is standing in front of a Pinhole camera. Now light coming through this object enters the pinhole. coming from the leg enters the pinhole. Now at the end of the day, the image of this object will be formed on the screen of the pinhole. But now you notice something, the image is upside down. Whenever your image is upside down like that, we said it is inverted. There's difference between lateral inversion. We will see that soon. So now, from what we have here, this hole that light is passing through allows us to form the image of this object on the screen. Now, the distance from that hole to this screen, we call it the image distance. That is your V. Then with the distance from this one, you need to understand this one because there are some technical questions they can ask you to solve here, and they just want to test your knowledge. The distance from, imagine something now, this, let me tell you what I'm telling you. From here to the pinhole, that is called the object distance. From here to this place, that is called the image distance. Now, the distance of the object to the hole is your object distance. The distance of the object from the hole to the screen is your image distance. But imagine I ask you this question. If I take this object from here, I move it to the back, or I move this object closer, do you think the distance from here to here will change? You have to think about that. Is that taken? Because when you are solving some calculations, you might need that knowledge. So no matter what I do to this guy has been built. So this is the screen. The only thing is that if I move it closer, the image might get bigger or smaller. If I move it further, same thing. So how do we now know that? In order to calculate the image height, so the height of this person is called the object height. The height of this person is called the image height. So if I want to get it, the image will get bigger or smaller, I use a formula called magnification. So magnification is image height over object height. It is also known as image distance over object distance. These are terms we should all have been used to. So this is called the image distance, this is called the object distance. This is called the image height, and this is called the object height. And magnification does not have units, because centimeter dividing centimeter, no units. So that is what we talk about. So,
sir, there's a question.
Yes.
What is responsible for the intersection of light from the sun before it reaches the earth, if the same sun rays can be intersected also directly on the earth's surface, when we know the distance between the earth and sun is constant?
It's constant. The distance between earth and sun. Now, if this is it, if the distance between earth and sun is constant, what we call the intersection is, if the moon is closer to the sun, what we kept constant is the sun and the earth. So that means the moon, you know, the shape of the earth is like this, eclipse, it's not round. So sometimes if the moon is here, it's closer to the earth. If the moon is here, it's farther to the earth. So now the moon, I don't know if you're getting this, the moon, if the moon is closer to the earth, then the ray will not intersect. Why? Because let's say this is the sun, this is the earth, and this is the moon. Now if ray is coming like this, do you think they will intersect? Let's now say the moon is here, and the same sun and the same earth position. If the ray is coming, it's because of the way I'm drawing, but the closer the moon is to the sun, the more it is to intersect. That is why that intersection happens, and that's why we have an exception. And that is majorly due to the shape of the earth. Do you get that? There's what we call the Kepler's law, how the satellite, which is the moon, continues to orbit the earth. So that's from Kepler's law. You will know that sometimes the moon can be closer to the sun and farther to the earth, and sometimes it can be closer to the earth and farther to the sun. So that is why they intersect. I hope that is clear now. So you can give a thumbs up if it is clear. So that is what we have. Now magnification is.
Someone said you should re-explain the pinhole camera.
I should re-explain the pinhole camera. Yeah. So it's fine. We don't really want to waste much time, but let's try and follow and get everything once and for all, so that we don't waste much time online and in class. Now, for the Pinhole camera, I said something. I said the image of an object is formed on a screen. Let's say this is the camera, and there's a tiny hole through which light can enter. I'm not done explaining though. There's a tiny hole through which light can enter. Now, when light enters the hole, then the image through this guy, you know, if light is coming from here to block it, so only light coming from this, a particular light comes from different sources. So as the light is entering the pinhole, on the screen, the image of this object, this is the object, this is the image. So the image of this object will be seen on the screen. And one thing is that if you now want to take the image distance, you always take it from the hole to the screen. So the distance from here to here is your image distance. We represent that with feet. The distance from here to here is your object from the hole. The distance from the hole to this guy is called the object distance. But I now say you should note something. Provided I'm using the same camera, the distance of the image will always remain the same. So if I keep changing this object, if I move it closer or I move it further, then the image will either be getting bigger or getting smaller. But the distance of this guy will not change. So there are some calculations that you might need to do, that you will say that when the object distance was u from here to here, the image distance was v. What will be the new object distance or whatever it is when you move it a bit closer at the particular value? You can just do your all these v1, u1, because v could be constant and they can give you their magnification, so you can relate that to get what you are supposed to get. So that is what that part is talking about. Now you need to now note something. Important points to note here. So when you are talking about your Pinhole camera, there are two major points you need to know. The hole must be small or tiny. The hole must be tiny. If the hole is too big, what do you think will happen? A lot of rays of light will enter. Abi? And from what we said there can be extended source or a point source. Abi? A point source will give a sharp image. There is difference between a sharp image and a bright image. Abi? If you can see the way this light is shining on me, it's looking brighter. And the more it looks bright, the more you cannot really, you might feel you are seeing me, but I might just be looking as if I'm bright, but not sharp. There's difference between something being sharp and something being bright. That's why sometimes you will say, oh, Abi, that means it's not so sharp the way the image is supposed to be. So it's not supposed to be white. It's supposed to just look normal. So if the hole is tiny, you are going to produce a sharp image. A sharp image. If the we have a lot to do. So if the hole is tiny, you are going to produce a sharp image. But if the hole is big, you are going to produce a bright and blurry image. So the image will be blurry, it will not be sharp when the hole is very big. And why? They can ask you that. The major reason you will have that is due to overlapping of images, because of much of the lights that are entering. So you can have an overlapping of images, and that will make everything blurry. So you need to think about that. So now let's move on from there. That's what about the applications of rectilinear propagation of light and shadow. So let's move on to reflection properly now. When you are through with that part, you should let me know. So let me quickly give you questions on what I've said so far. So you have to answer true or false in this question. 1. Magnification of a Pinhole camera. Magnification of a Pinhole camera is always 1. So you have to answer true or false. The magnification of a Pinhole camera is always 1. True or false? A pinhole camera, I need to do some bit of calculation to give you this, but I want to make it technical. A pinhole camera, just let's understand it, as an image this produces an image distance of v. Okay, that's good. When an object is placed at a distance u, if the magnification is 3, well, still say like image size is 3, just to put it in a plain language. If the magnification is 3, find the magnification when the object is placed at a distance, when the object is placed at a distance 3/4 of u, 3/4 of the initial distance, just to make you think about something. So number 3, that's number 2. Number 3, the image height formed by pinhole camera. The image height formed by pinhole camera is 10 centimeters. If the image distance is 200, if the image distance let me give it as 200, increase the distance 20 centimeters. If the image distance is 20 centimeters and object distance is 10 centimeters, find the object's height. Find the object's height and give a comment. On the magnification. Find the object distance and give a comment on the magnification. Number 4. Moon is an artificial source of light. True or false? Moon is an artificial source of light. True or false? Number 5. Arrange the following in order of increasing wavelengths. Arrange the following in order of increasing wavelengths. red, indigo, blue, and green. Arrange the following in order of increasing wavelengths: red, indigo, blue, and green. So quickly, number 6. A wave a visible light emanates from a source of frequency 200 kilohertz. What is the wavelength of the wave? Without wasting time, so we can deal with these questions. So let me dictate it again because of those online. You have to answer true or false here. Magnification of a Pinhole camera is always 1. True or false? A Pinhole camera produces an image distance of V. So this is more like number 2. This is like your number 1. So a Pinhole camera produces an image distance of V when an object is placed at a distance U. If the magnification is 3, find the magnification when the object is placed at a distance 3/4 of U. Then number 3, the image height formed by a Pinhole camera is 10 centimeters. If the image distance is 20 centimeters and object distance is 10 centimeters, find the object's height and give a comment on the magnification. Moon is an artificial source of light. True or false? Arrange the following in order of increasing wavelengths. So that's all. So let's move on to reflection of light as plane and curved surfaces. We have the first right. Some people have already started giving their answers online. So if you have your answers, let's see. What's your answer? Let's see. So if you have your answers online, you can give your answers. So Okola already calculated for number 6. Have you done for number 6? Yes. What did you get?
1.5 times 10 raised to power 3.
So they also got 1.5 times 10 raised to power 3 meters. Did you all get 1.5?
Yes.
If you did not, you can let me know so I can solve it. So number 1, is the statement true or false?
False.
Okay, so some people online too said false. Number 4, did I ask you? Number 4, is the statement true or false?
False. False.
The statement is false. So, but someone said true online. Then someone has arranged them red, green, and blue. So let's move on. So the statement is false. This is an artificial non-luminous source. Actually, artificial source, it's a natural non-luminous source. So not so the statement is false. Is that taken? So how do we arrange this? Which one comes first? Which one comes first? Okay, someone arranged that already. Indigo, followed by blue, followed by green, and followed by what? So just remember your Roy beam. That will tell you, and I told you it ranges from 400 nanometer to 700 nanometer, but red is the one with the highest wavelength, which is around 700 nanometer. So can we go on? So online, can we go on with the class now? So, you know why I set questions like this at times, so that it's more like helping you to read. Think about what I've said again. That's something like flashcard, trying to paint the picture of everything I've said as a scenario again, and that will make it to stay. So if you now go and pick your own questions, you can start practicing. So let's quickly start with reflection of lights at plane and curved surfaces. Sorry if the light is disturbing, but just manage. So let's look at reflection of light. At plane and curved surfaces. So we want to quickly look at reflection of light at plane and curved surfaces. So the first thing you need to know is what is reflection itself. What is reflection? And we all know. So the first statement is reflection. Reflection is a part of those properties of waves. So if I kick a ball against a wall, the wall will send the ball back to me. So the wall will reflect the sun. As the light is shining on my face, I'm reflecting the light back to you, so you can see me, depending on the angle at which the light strikes my face. So when you're talking about reflection is simply sending back of wave or light when it strikes a surface. So when light strikes a surface, then the light will be sent back. That's reflection. It's not a new statement. But now, when you're talking about reflection, we have three major rays that are important that you need to always know. We have a ray called an incidence ray. If you are a starter, there's what is called an incidence ray. An incidence ray is the ray that is coming from the source. The one that is striking you is what we call the incidence ray. Then we have what we call a normal ray. Normal ray is what you need to take note of the most. It is usually perpendicular to the surface. So if I have a surface like this, then ray of light is coming from a particular source, just like when a ball is coming. When you hit the ball against the wall, then the wall will hit the ball back. at the same angle. So how do you determine the angle? You need to draw what we call a normal. So the one that is coming from a source is called your incidence ray. The one that is perpendicular to the surface, that means at 90 degrees to the surface, that's what we mean by perpendicular, is called the normal ray. While the one, this ball now will bounce off at the same angle at which it hits the surface. Then that one that is sent back is called the reflected ray. So the third one is called the what? The reflected ray. Is that taken? So we have the incidence ray, the normal ray, and the what? The reflected ray, which you need to take note of. But don't forget that your normal ray is always what? Perpendicular to the surface. Now we have two types of reflection. So we have types of reflection. First is what we call your normal reflection, diffused and what? Regular. So we have what we call regular reflection and we have what we call irregular reflection. Regular reflection happens when you have a smooth surface. So when the surface, that means the screen that you are hitting is very smooth. Then we have the regular reflection. Then you have a rough reflection when you have a rough surface. So irregular reflection happens when you have a rough surface. We are going to see the two. Now, when the surface is very smooth, the moment the light strikes the surface at a particular angle, then the light will be sent back at another angle in a regular manner. So if another one strikes, it will be sent back in a regular manner. But for a diffused, we also call irregular diffused reflection. So for a diffused reflection, if the light strikes, this will be sent back based on the surface. So that is what we call diffused reflection. So it happens in Yoruba and English. So when you have a raw surface, you know there's a ray of there's a ray of light coming. The arrow shows you the one that is coming. This one shows the one that is leaving. So when the ray of light strikes the surface, it is sent back. If I use this one to also strike, it's also, you can see that all these ones follow a particular same pattern, all because the surface is smooth. When the surface is rough, you know, if the ray is coming like this, look at where it strikes it, because that place goes up, so it will send it back like this. If it's coming this way and it hits this place is like this, you know, it's like if you hit ball against this, that surface will send it like this. Something like that. So because the surface is rough, so anytime the ray strikes the surface, it goes in different direction. So that's what we mean by diffused or irregular reflection. Can we move on? So now, with this, you need to know what we call the laws of reflection. So what are the laws of reflection? Since you already know the rays, the first law is that the incidence ray, the normal ray, and the reflected ray, they all lie in the same plane. So your plane y, x and y. So you have your incidence ray, you have your normal ray, and your reflected ray, all lie in the same plane, all work together. So the next law states that your incidence angle will be equal to your reflected angle. That's another point you need to know. So what do we mean by incidence angle? So in case you are still writing, let's be fast about that. Yeah. Are we following? Yeah, so I can quickly talk about it. Please, I'm doing this because by on the 13th, when I'm coming, I want to believe you have done it. That's why we are doing it, in case you just join. So if I'm coming by that time, I'm coming to solve questions, I'm coming to talk about some deeper parts for some schools. We just keep solving questions. That's what we are coming to do. So you two, you should keep practicing. so that you know it will not be as if we were not taught, and that's why we're quickly taking our time to teach everybody together. So just some important part that I know that my students need for the purpose of the exam. So I will not start teaching those people. Let's start solving the exam, start looking for problems, start causing trouble to the day of the exam. So the UI people on the 25th will usher you to the exam. When is OU? Have they announced the exam? So their own might be after you are away. So that we start solving all the necessary questions. So what can we move on now? What do we mean by incidence angle? Reflected angle. The angle, you know this incidence ray now. What did I call this line? What did I call this one? Normal ray, Abby. Then I call this one what? Reflected ray. That angle between the normal, the angle between the normal and the incidence ray is what you call the incidence angle. Not between the incidence ray and the mirror. So there's an angle between this normal and this incidence ray. That angle is called the what? The incidence angle. The angle between the normal and the reflected ray. That angle is called what? The reflected angle. Is that taken? And law of reflection now says that the incidence angle will be equal to what? The reflected angle. Are you okay now? So now, from if you understand this, then we need to understand some things. We have what we call incidence angle, reflected angle, glancing angle, and deviation angle. So let's know the difference between the four. Incidence angle, glancing angle, reflected angle, and deviation angle. So now, glancing is G-L-E-N-C, like glancing. Then deviation. We already know how to spell incidence and reflected. So can we start? So now, if you have a surface, ray of light is coming from a source. When the ray of light strikes the surface, that ray is called the incidence ray. Abi? Now, if this is the normal to the surface, we said the angle between this normal and the incidence ray and the normal ray is what? The incidence angle. Abi? That's settled. Then the angle between the reflection, we already said the incidence ray angle will be equal to reflected angle. So this I must be equal to this place. So the angle made by the normal and the reflected ray is called the what? The reflected angle, which is a straightforward thing. But what do we now call these angles that are left? The angle made by the ray with the mirror, either the incidence ray or the reflected ray with the mirror or with the surface, we call it the glancing angle. Is that taken? So the angle made by the incidence ray with the mirror or the reflected ray with the mirror, that angle is called what? The glancing angles. Are you following? Now, let's look at this. As the ray of light is coming from a particular source, the ray strikes the surface, Abi, and it was sent back. But what was the mission of this ray? To go like this. It was going like this, Abi. What made it to turn back? Because it strikes a surface. If I kick a ball, the ball will continue to move, except it hits something. So the purpose of this ray is to continue. But because of the surface is strike or stroke or striking, it was reflected. So now the ray was determined to go this way. So it has deviated from its normal path. So it has moved away from where it was going. Do you understand that? So now, instead of going straight, it is like this. Then we call this angle the deviation angle. So it has deviated from its normal journey. So that is called the angle of deviation. Is that taken? So now, we remember something. What is the angle on a straight line? You know, if I continue from here round, that will give me angle on a straight line. Abi? But you look at from here to here, That's your higher now, Abby. So I can say the total angle on the straight line is equal to what? 180 degree. So 180 will be equal to I plus R plus D. Do you agree? You know from here to here is I, Abby. From here to here is what? R, Abby. And from here to here is D. So the total angle on that straight line is equal to what? 180. Do we get that? So now, what is my R and I? They are the same. We already said from the laws that the incidence angle will be equal to what? The reflected angle. So I can say that I is the same thing as R. Since I is equal to R, then I can say 180 degree is equal to 2I plus D. So your D is going to be 180 minus 2I. So they can say calculate the angle of deviation and they give you the incidence angle. If they give you the incidence angle, then you can get your deviation angle. Is that taken? So let's move on. One thing you also need to note is that this deviation angle is also 2 times your glancing angle. That's 2 times your glancing angle. So let me give you a quick question on that. So drill. Solve this out. So if you're online, solve and drop the answer. So the first question, number 1. A ray from a source, or you can just turn it so that maybe they write the details. So I'll drop the question and quickly solve. I'm waiting with your truth and then.
Wait. Is this something bad? Something bad. Something related to. Something related to.
I've not seen that girl.
Yeah. Oh, it's also should have specific.
So let's solve this question. I'll give you just like 2 questions. The ray of light from the source makes an angle of 35 degrees with the mirror. Determine the glancing angle. Determine the deviation angle. Determine the deviation angle of the ray. Number 2. 2 mirrors placed perpendicularly to each other. If a ray of light makes an angle of 30 degrees with the normal on mirror 1 or mirror 1, what is the angle of reflection in mirror 2? Two mirrors placed perpendicularly to each other. If a ray of light makes an angle of 30 degrees with the normal on mirror 1, what is the angle of reflection in mirror 2? Can we start? Oh yeah, can you solve? I want everybody to solve online and drop the solution. I will quickly solve this one for you so that we understand this better. So the first question is, a ray from a source makes an angle of 35 degrees with the mirror. Determine the deviation angle of the ray. So the second question is, two mirrors placed perpendicularly to each other. If a ray of light makes an angle of 30 degrees with the normal on mirror 1, what is the angle of reflection in mirror 2? And the angle of deviation? So you have to calculate the angle of reflection and angle of deviation. Aisha, yes. E equals to 2G. I will explain that with this question. So someone said, why is D equal to 2G? So we are going to see. I will explain it soon. So quickly leave your answer in the comment section. And don't forget to subscribe. That's the only thing you can do to help the channel. Subscribe. So keep subscribing to the channel to help the channel and to get more followers, and keep sharing and keep making your comments. The video will be uploaded. If there's a part in which you can watch it again to understand it better. So are we true? Everybody wants the answer to number 1? 70. Do we all got 70? Did you all get 70? No. Okay, if you didn't get 70, we'll look at it. What did you get? What did you get? 110. We'll look at it. One person will be correct, one person will be wrong. And there's a reason some of you will be wrong, which I will tell you. I don't know which correct and wrong, but we'll solve it too. Number 2, what's the answer? 30. 30. Okay. So let's see. Can we solve this now? So let's quickly do the solution.
I know. But it's 2 mirrors. That's what I'm asking.
Now the question says what? Please everybody listen. The question says a ray from a source makes an angle of 35 degrees with the mirror. Determine the deviation angle of the ray. The angle of deviation. Look at the statement. The ray is coming from a source. And another ray was coming from a source. What did he strike? At what angle is it to the mirror? At 35 degrees with the what? The mirror. Is it with the normal or with the mirror? So you have seen. So you have to be careful when you are solving questions. And funniest thing is the answer you have gotten will be in the option. And you'll be thinking like the exam is very soft. And you get out of the exam hall, they ask you how was your exam? Soft. Chop chin. Small thing, we did it well. It's very simple, but you missed a statement. And that's why you should learn to read through the lines. So the question says that a ray of light from a source makes an angle of 35 degrees with the mirror. So the angle made with the mirror is 35 degrees. So that's the glancing angle, Abby? Yeah. So now you withdraw your normal. What are you have to do for deviation, Abby? And you know your deviation formula, but let's not even solve it yet. But you could have just used your deviation, which is equal to 180 minus 2y, Abby. But you are talking too much. Thank you. Now, if you had used 35 as your eye, then you would have been wrong. Abby, what will be your eye now? You know we said that this normal is always 90 degrees. Abby? So if from here to here is 35, what will be from here to here? Let me call this place alpha. Like a math. So we'll say that since this place is 90 degrees, then we're going to have 35 plus alpha. Abby. So alpha is going to be 90 minus 35. And that's going to be 55 degrees. So your high is 55, not 35. That's where some of you might have missed it. Do you understand that now? So now, that means your reflected ray will also be 55. If you already know this, you could have just said 2 times 35 and you get 70, which will be correct. But now, putting high into this place, then you will have 180 minus 2, 55. That's 110, and that's 70 degrees. So the deviation angle is 70 degrees. You can check it out yourself, but we don't have time to waste. Do you understand this now? So let's look at the second one. So the first statement says that we have 2 mirrors, and the 2 mirrors are placed perpendicularly to each other. Abby? So that means that there was one mirror that was like this. Anyhow you place it, if you like, put the second mirror like this. So you can place the second one like this. Perpendicular means that the angle between them is 90 degrees. Is that taken? So this is the first mirror. So let's call this mirror 1. Let's call this mirror 2. So they are placed perpendicularly to each other. Can we move on? So if a ray of light makes an angle of 30 degrees with the normal, you can see the statement here now. Is it with the mirror or with the normal? So that means for mirror 1 now you draw your normal. It must always be perpendicular. Abby? So this is our normal. So if a ray of light is coming from the source, my hand is very straight. So it makes an angle of 30 degrees with the normal. So what will be the reflected angle? It will also be what? 30. You know, it is that reflected ray now that will not be the incidence for this. So this place will also be what? 30 degrees. There are different ways in which you can solve this, but if you understand some basic mathematics, it will be faster. But if you don't, you even need to understand basic mathematics. This will be the new normal, for mirror 2. And the angle of incidence here will be the same as the, and they say you should look for the angle of reflection in what? In mirror 2. Do you get that? So now, if this place is 30, what will this place be? You know this place is 90. Angle, total angle, your triangle, 180. So if this place is 60, 90, what will this place be? And this place will be what? You understand that?
Yes.
So for you could have also done it this alternate. So if this place is 60, this place will be 60. This place is 30, this place will be 30. Alternate and who are what? Equal. Or you could have just said that 60 plus 90 like 180 minus 60 plus 90. That will also give you this place. Do you understand that? So now if this place is 60, what would this place be? And that is your answer. So now that we know what reflection is, we know glancing angle, we know incidence angle, and we know all the things we need to know. We said that how did we know that this place is 2G? You have even confirmed this now. Aisha, what did we get as the deviation here? 70. So if you say 2 times 35, so you can say, and what's your G? 35. Do you understand this now? This is 35. So which means that deviation is just this place plus this place. If you put it like this now, that has a real mathematics. You don't have to hear when you put this place and this place. So your deviation is 35 plus 35. Or just say 35 times 2. That can also give you deviation. So are we settled? So now, all this reflection brouhaha is not a problem. We are just starting. What you buy? Oh, you have solved it yourself. Yes. But you should have understood it. Let me solve it again. So the first mirror, the second mirror, this one makes an angle with the normal 30 degrees, and this makes an angle which is going to also be 30 degrees. And if this place is 30, this place will be 60 degrees. Since this is perpendicular, it's going to be 90 degrees. Total angle in a triangle is 180. So this place is going to be 30 degrees. Then this place will have its own normal. If this place is 30 degrees, then this place will be what? 60 degrees. Then if that is 60 degrees, then this will also be what? 60 degrees. And that's what I've done. Share you get. Can I rub the ball? So let's talk about mirrors properly. Mirrors. Because I've been using the word mirror. So we then want to look at reflection at plane and curved surfaces. Yeah, can I rub it? So let's quickly look at mirror summary. Don't worry. I'm time conscious to this is 11:49. So however it is, if we don't finish this today, please let's cover all the important parts. And this part is very important. So for mirrors, we have two types of mirrors. We have what we call a plane mirror. Plane mirror just means straight. You always paint one side in a mirror. There's none of you in this place that won't have seen a mirror before. And if you paint one side, you look at one side. If you did not paint one side, you will not see anything. Because it's the part you have painted that did not allow the light to. You know, it says it can be transparent. Glass is transparent. So if you're looking at a glass, you will not see yourself normally. But if you paint the back, there would have been refraction a bit. Then that will now send the light back to you, and you can now see yourself. So that is what mirror does. So you have to paint a side, and you leave a side clear. Do you get that? So now we also have what we call a curved mirror, or a spherical mirror. There are three major types of these mirrors. We have what we call a concave mirror. We have what we call a convex mirror. And we have what we call a parabolic mirror. The most important thing is that we paint one side. We paint one side. One side is the side that reflects. So if I'm shining light now, I have to shine it on the reflecting part, not on the painted part. So now, for concave mirror, the difference between this and this is that you will paint you have a mirror that is curved like this, then you paint the outside. So every time you look at the mirror, you look at the inside. You have a mirror that is curved like this, you paint the inside. That's just the difference. Every time you are looking at this mirror, you look at this side, not inside. Cave means inside. So that's how you always remember. So if you're looking at me directly, I remember. That's how I remember. So while talking now, immediately I say concave, I already know it's the inside I'm looking at. Is that thinking? It's not everything that English will teach you. You have to understand it. Parabolic is a form of concave mirror, but it's just that it is more curved than concave. Parabolic is a form of concave mirror, but it's more curved. There's a reason for that, which we'll talk about at the end of the class. Once you understand the principles, you might not really get that part. So now, for a concave mirror, the inside is the reflecting surface. For a convex mirror, the outside is the reflecting surface. Is that taken? Your concave mirror is also known as converging mirror. You don't need to cram it. You will know why as we are moving on. Because there are two different things. So the God of Refraction, you must not misplace them. But as we are moving on, you will know why we also call it converging mirror. So a concave mirror is also called what? A converging mirror. Then we also have what we call a convex mirror. A convex mirror is also known as what? Diverging mirror. Diverging mirror. You will know why we call it diverging as we move on. Because our first attention will be on plane mirror. I want to be fast about that. What did you say, Aisha? The second concave mirror is a diverging mirror. I understand. I did not cram it. I'm sure of what I'm saying. I'm 100% sure. It's a converging mirror. Concave mirror is a converging mirror. You are the one that is doubting. For me, I'm not doubting. Are you sure of what you are saying? Or is your textbook saying diverging? If your textbook says diverging, I want you to see that. The reason is this: any ray that is coming like this will converge. So it's a converging mirror. Any ray that is coming like this, they will diverge. This one, if I trace this one, you know I talked about diverging rays. So it will look as if they are coming from a particular source. But this one, if you trace this one, it will look as if they are coming from mid-30 points. For length, yes, it's opposite. So a concave lens is a diverging lens. So let's move on. So now, when you're talking about plane mirror, that's our first focus. Plane mirror. So for plane mirror, let me see if I can get another one. So, for plane mirrors, it's not so hard. First thing we need to know about plane mirror is just characteristics. We have, so you need to know the characteristics of images formed. Images formed in a plane mirror. That is, when you are looking at yourself in a plane mirror, what are the things you notice? So this is a plane mirror. So let's summarize the characteristics. If you have a plane mirror, my dear, if you are looking at yourself, does your head get bigger?
Yes.
Except you are a cat, you are saying, I am a lion, I am in the boss. The only thing is just that from year to year, the object's distance. I mean, we already said the distance to the mirror is the object's distance. From here to here is the image distance. Is that taken?
Yes, sir.
This is the height of this guy. This is the height of this guy. Are you following? So this is you looking at yourself in the mirror. Is that taken? So now the first thing is that characteristics. Your distance to the mirror is the same thing as your object's distance to the mirror. If you are writing UI, you must know how to use relative velocity here. Relative motion. So U will be equal to P. Image distance is always equal to what? Object distance. You cannot be looking at yourself in the mirror and your image will be far away. People are not fighting. You stay far to your image stay far from you. You stay closer, your image stay closer. So that is what we say. Are you following?
Yes, sir.
So now, another thing you need to know is that your object height will be equal to what? Your image height. Is that taken? You can't be taller than who you are in the mirror, except you believe in yourself. That's the only thing. Oh, Gawa, wo mirror. Oh, legacy. You cannot be taller. Nika, I'm not talking to you, neither am I talking to Victoria. She gets. But just talking pieces. So, but one thing I know is that irrespective of your height, anybody that is taller than you is too tall. Anybody that is shorter than you is too short. You are the one that is normal for your level. So, number 3. Are you there? So, you need to know. I will ask you a question soon. If you do your hand like this in the mirror, what will the mirror do back to you? But in the mirror, you will not see it as right hand. You will see it as left hand. And you'll be surprised that you are not fighting. I'm throwing right, you to throw right. It's a lie. It's always throw left. So everything you throw right will be flipped to left in a mirror. So that means that we call it lateral inversion. So the image in a mirror is laterally inverted. Is that taken? So now, this is an example of lateral inversion. Everything right turns left. So if I put J like this, the way J will look in the mirror is not like this. It will flip. That's called lateral inversion. Do you get that? You can't see. If you do like this to a mirror, this is the mirror, and this is you. The mirror too will do like this. So that is called lateral inversion. This one is one, but it's not called. Problem here. Yeah? So, is this how your own bubble looks like? Is bubble now hexagon? Go. So, let's move on. So it is said to be laterally inverted when it flips over. So that is the thing. You will not do bum like this, and this one too will not go like this. That's why it's gone.
Sir,
So
someone said it does not understand the lateral inversion.
lateral inversion. If you are in this class and you are going asking the question that you know that I cannot answer us alive, ask where's the duster? Please, lateral inversion simply means flipping, turning right to left. That's just what it means. Flipping. So if I have this now, if I have B in the mirror, how will B look? It will flip in the mirror. That's what it means. So that means that B will become, that's what we mean by lateral inversion. If I have C in the mirror, C will become, that's lateral inversion. A quick question, then you leave your comments, or you cannot leave comments, or you cannot draw. So, but you can still leave comments. In this case now, if I draw this, everybody, how would this look like in the mirror? We are draw the mirror image in your notes. So what will be your answer? So if you flip this in the mirror like that, what will be the mirror image? So lateral inversion is flipping. What's that? So the question that we ask everybody, and you should drop your answer in the comment section. Which one will come first in the mirror? If I see online and you deleted the message you have sent, I speak, I will look for you and I will sue you. If you are in India, I will be in India tonight. In Nigeria, we have something like this. We can fly with wings, and we can fly with mass, and we can fly with drones. So, now it's going to be, we will come first because object distance must be the same as image distance. Then P is farther, so P has to go farther. So P, but P will also flip. P will look like this. So that's the answer. You have missed it, Abby. Hallelujah. Lateral inversion does mean flipping. So B will come first, then followed by P because of the distance to the mirror. She gets. So you have to obey this one and obey this one. Is that clear now? Another thing you need to know is that image formed in a plane mirror is always virtual. It is virtual. I'm not going to teach you how to draw images in plane mirror. You could have done it. I can quickly do an example now, but it can turn some of your head. No post you tell me we ask you that. But even if they do, maybe I'll quickly show you. But there's no time, so I'll show you. So now, image formed in a plane mirror is virtual. And what does virtual mean? It means that the rays of light that form the image, they are not the actual rays. They are not the rays coming. They are imaginary rays. Most times you hear that it is because it is formed at the back of the mirror. That's true, partially true. There is nothing like back of lens or front of lens, but it can still be true for mirror. But for lenses, even the image can be formed on the same side and it will be virtual. It depends on what it is. Even in mirror, I think image is even formed on the same side too. That is virtual. True of us. No. So it's still at the other side of the mirror. It's not the same side. So let's move on. We'll get there. I just wanted to tell you something. Get myself wrong. I said it's So please, we'll get what this means later as we are moving on with the class. It is real when it is the actual rays that meet. It is real. It is virtual when it is an imaginary ray that meets. Then when it is formed on the other side of the mirror, not lens, it is real. But for lens, it can either be real or so we'll get there. So, but for plane mirror, it is always virtual. Your image is imaginary. Number 5. The magnification of your image in a plane mirror is usually 1. Magnification is always equal to 1. So let's move on. Now that we know images form in a plane mirror, characteristics of images form in a plane mirror, I don't want to do that, but let me just do it. Now, this is an object. I want to see this object in the mirror. I'm looking at it. So I will draw 2 perpendicular lines from the end of the object. I'm just saying it briefly for those that want to remember. So I will draw a perpendicular line to the mirror. Then I will draw a line to show that the object distance is the same as the image distance. Then the eye that is looking at it, I will draw a straight line to the eye. So look at it, that's why we say virtual. You will see the word virtual now. So I will now trace this line down to the eye. Because I'm drawing, I have the right to adjust my eye. So that's what I have. But what really happened? This guy will be looking at this guy as if he's coming from here. Whereas that's a line. This guy is actually coming from here. So because if you will now trace this line now, this one, that is incidence, normal, reflected. Can you see that? This is incidence, normal, and reflected. Can you see that? So what this person is seeing is the reflection of this one. But to this person, it seems as if it's coming from here. So the rays that actually form this image, they are not the rays. They are this person's imagination. Do you get that? So it's coming. That's why we say it's virtual, because the ray just strikes the mirror, then come back. The ray did not enter the mirror. So, but this person is seeing it as if it's actually coming from here. So we said that this image is virtual, because the rays that form it are not the actual rays. So let's move on. So now, the thing you need to also know is what we call arrangements of mirror. Or before that, let's say arrangements of mirror. So in arrangements of mirrors, what you can do is that you can place mirrors together. So let's say you place 2 mirrors like this, like the other one we did. These mirrors are said to be at what angle to each other? 90 degrees. If I place one mirror like this, and I place another mirror beside it, they are at what angle to each other? This is at 180. If I place one mirror like this, and I place another one like this, they are at what angle to each other? They are at no angle. So we said it's 0 angle. Like the one you have in your salon, your mirror, when they are making your hair, and you continue to see yourself continuously. So now, for all of this,
And it's just water. You examine this is you know what the calculation if I say you the wife what be you should be Any clear for you? I don't know. But yeah.
Sorry, I was kidding.
So sorry about that. So arrangements of mirrors. When you arrange mirrors, you can say calculate.
Where is Miriam?
I'm gonna be the original one. You're in class. Can't see.
So they can say, look at these two mirrors I placed now. If I have an object here, if you are looking at yourself in this mirror and you are standing somewhat like this, between them, somewhere you are standing and the two mirrors are placed like this, you only see yourself in three places. You will see yourself here. If I draw it, you will see. You also see yourself here. I used to play with everything. I will draw everything. So you will see yourself here. So when you look at yourself, you see yourself 3 times in the mirror. And how did I know this? I can calculate it. So the formula you use to calculate the number of images is n is equal to 360 over theta. I always like to put brackets because students make mistakes. Minus 1. What is the angle at which I play there? So if I want to calculate my number of images, that would be what? 360 over 90. 360 divided by 90 will be what? 4 minus 1. So I will say 3 images. Is that taken? So that's what we have. If you place them at 180, you will only see. Because if you are standing and you are looking at this guy, it is just like you are looking at one mirror. Abby? So it's still like one mirror. So you only see one image. Do you get that? Because 360 divided by 180, that's going to be 2. 2 minus 1, 1. Then for this one, if you look at the mirror, you are sitting in between them. The image you look, you will be seeing yourself continuously. So that's what we call infinity. So you see yourself as infinity. If you do 360 over 0, that's not infinity. I mean, infinity minus 1 is still infinity. Do you get that? So now that we know that, can we move on? So the next thing is that although this arrangement of mirror has its application, so the quick application without wasting time is that since we can arrange mirrors together, we now find application in periscope. Normal mirror periscope. In mirror periscope, you have an instrument that looks like this. Then inside the instrument, you have something like this. So if you place an object on a tall place, let's say this is a ball, that ball is placed and this is you, you are like Victoria, so you cannot really see the top of the roof. So all you can just look at is that Victoria will look on the imaginary. So now you need 2 mirrors. Place one mirror here at 45 degrees to the frame. Then you just place another mirror. So Victoria will check right. So you place another mirror here in case the battery will. Those days when we were young, our grandma would say we should go and bring plates on top of shelf. There is a place for visitor. There is a place for most important visitor. There is a place for very, very special visitor. All those drama. There is a place for daddy these days. So that with daddy can go jam. They jam the pots. There will be golden plates. There will be golden spoon. Everything. Then there are some plates that if you drop it once, just know that your life has finished. Immediately you drop that plate and grandma hears, just follow that plate and crash. So, like that. Now, the ray of light coming from this ball will strike the mirror. By the time it strikes it, this mirror will send a reflection at an angle to this mirror. Then this mirror will send the reflection back to your eye. So at the end of the day, this object will now be seen. Let's say you are shorter. Okay, let's say you are drinking. So now, you now realize, oh, this is the ball that mommy said we should not play. See, this is where mommy hit the ball. Then you will see it through the mirror because you have the third science. Then you now go and look for stool and climb. You now fall down and like that. So for periscope, that is how it works. So they can ask you, you use periscope to see objects that is above the normal eye level. That's the use of periscope. Is that thing? They use it in war too. Imagine that you are in a tank, water tank that is moving, and you feel like you are very good. People are shooting at the front. They are at the front with their guns. They are shooting, and you now come out of the tank and you say you want to see people shooting. You know that song that those people used to sing when they be carrying caskets. So, but you could have just used your periscope to look at them. And that's one of the things that periscope helps us to see objects that are beyond our eyes. So let's move on. The second application is kaleidoscope. People are talking more than the classroom. So another application of play mirror is in kaleidoscope. Kaleidoscope is a toy for babies, for children. But if I see it and I still want to play with it. So kaleidoscope, the mirrors in what's the angle at which the mirrors of periscopes are placed? The mirrors in kaleidoscopes are placed at 60 degrees to each other. So there's a way it's arranged. We don't have much time to start talking about that. So it's a mirror. They can ask you that the toy that is played with by mirror, by children, toy used by children. So that is what we call kaleidoscope, and it forms multiple colors in case they ask you. So they will be looking at it and be rotating, and there are a lot of gems inside. And when they are rotating, not the camera, that camera you just click, that one will switch. But this one is kaleidoscope. When you look at it, you rotate it, all the gems inside will be mixing, and you'll have be forming different color patterns. And those color patterns will look very beautiful. So we keep playing So, can we move on? Another part you need to understand is what we call rotation of mirror. Mirror rotation. So, how do we form rotation of mirror? You need to note something. When the incidence rate is constant on a mirror and the mirror is rotated at angle theta. When the incidence ray is constant on a mirror and the mirror is rotated at angle theta, the new reflected ray rotates at angle 2 theta. When a mirror is rotated at angle theta and the incidence ray is kept constant, the new reflected ray will rotate by 2 theta. That's a rule. You can derive that rule, you can find it yourself. But let's see how it is. It might look a bit confusing. I'm not going to waste time on it. So pay attention if you want to really understand what we are doing. There's nothing much. Just understand what I've said here. And that will help you to already solve your problems. So in that case now, this is the mirror. So let me call this mirror 1. There's an incidence ray on this mirror. Then there's the normal. I hope you're following. Let me call this incidence ray. I'm not going to change the incidence ray, it should remain like that. And let me call this M1, meaning that number 1. Let me make this one smaller so that the mirror can be, the board can take it. So this is the incidence ray, this will be normal, then this will be the reflected ray. Let me call that R1. So this now says that if I hold the incidence ray constant, that means I did not change the position. Maybe I own a laser, I let the laser be there. So I did not change the position. Constant on the mirror, and the mirror is rotated at angle theta. So I now rotate this mirror. I turn it like this. Shall you get? So now by the time I rotate it, let's say it's now in this new position. That means I move it from here to here. Do you get that now? Through what angle now I rotated it through theta? Do you understand that? Why the incidence ray is still the way it is? Then I will notice something. I will notice that this my reflected ray would have gone, while this one is still remaining. Like this is now the new incidence, then this will be like the new reflection. Shall you get? Do you understand that? Like this, the incidence I did not change, Abby, but it's almost like the way it is. Don't worry, just get this so that we don't waste time. Now, initially, this mirror was rotated through theta, then the normal 2 will be rotated through theta, which what we have done. So let's call this M2. Then the reflected ray would have actually either come inside or very close. Then the R2 would have gone from. Let me rotate it to this side so that the R1 can, because if I do it like this, it's like R2 should fall this side. Shall you get? And it will not make the image look okay. So let me rotate it. Let me restart. This is what I'm saying. Let's say this is the mirror 1. I'm not actually supposed to be explaining this. I did not plan it to be because of time, but for your sake. So let's say this is our mirror 1. Now let's follow again. This is the incidence ray. Please let's follow. That's high. So let's call this number 1. The point you have to note is that if I now rotate this mirror, I want to do it this way so that it will shift like this. Do you get that? So now I've rotated it through theta. Normally for the first mirror 1, there is an angle of reflection, Abby, which is R1. So by the time I rotate it through theta, this R1 would have also, you know, this ray is like this now. Look at this this incidence ray on the second mirror now, or mirror 2. If I want to draw the reflection for that, you know, it will look somewhat like this too. Abby. So now that means this would have gone from R1 to R2. Why I remains the same for both mirrors. The eye that produces R1 or mirror 1 is the same eye that produces R2 or mirror 2. Do you get that? So this statement is saying that if I rotate it through theta, my R will go from R1 to R2 by 2 theta. That's what it means. So if I rotate this one through theta, the R1 will go from R1 to R2 by what? By 2 theta. So if I say a mirror is rotated at 10 degrees, what is the new reflected ray? That means new reflected ray will be 20 degrees. But sometimes for some analysis, you need to understand why. But we don't really have time for that. When I come for next class, during our questions period, there are a lot of questions on this, so we'll solve them, so you understand them. I will calm down then. But for now, there are a lot of things for you to learn. Let's learn them. Then we can come back and start dealing with problems. Do you get that? It's a different thing, you don't know anything, and you are dealing with what is difficult for you. But it's very simple, we can prove it, we can derive it and all. If you rotate through theta, normal 2 will rotate. Let's say the normal for this one now, you know it will be perpendicular. Normal 2 will rotate, so n2 will become theta. If you rotate by theta, n2 will also become theta. That one is straightforward. If I have this was the first mirror. So if you look at this was the first mirror, it was like this. This is the normal perpendicular. If I rotate this one, definitely normal 2 will go with it. So as I'm taking this one, normal will be following it. So if I rotate it through theta, normal 2 will go through theta. That's what that part is just saying. So they don't need to tell you that common sense is what will tell someone that one. So, but the one that they feel common sense, you might need to derive is what they have said. But we will get it. The only thing you just need to do for me is just understand this first. That if you have an incidence rate N constant and the mirror is rotated through theta, the new reflected wave will rotate through what? Through theta. Just know that. So I can give you a question on that when we are through with everything. So now, let's move on. I think that's all. I think that's all on plane mirror for now. So, quick questions on plane mirror. So I'm trying to, there was a question that came to my mind when I was teaching something. I felt, let me leave it to the end. Now I forgot. So that's why I want to go through the Okay, the question is fine. So let's start. Number 1. Number 1. You still remember this formula? 1 over f is equal to 1 over a plus 1 over b. So, come back to that. So this question. Question 1. So you leave your answer in the comment section. The ray of light strikes a mirror at 30 degrees. Determine the glancing angle, reflected angle, and deviation. The ray of light strikes the mirror at 30 degrees. Determine the glancing angle, reflected angle, and deviation. Number 2. The following are attributes of plane mirror, except A, U is equal to B. B. Image is inverted. C. Magnification is 1. D. Image is inverted, magnification is 1. D. Image height equals subject height. E. None of the above. That's number 2. Number 3. JP stands in front of a plane mirror at an angle at a distance of 10 centimeters to the mirror. To the mirror. If his image height kini distance ruler 10 centimeters. If his height is 2 centimeters,
So we are fighting without getting back together.
determine is, let's just leave that 2 centimeters. If his height is 500 centimeters, might as well pay 200 centimeters. Determine his magnification in the mirror. Number 4. Ashiats standing at a distance of 2 centimeters to a plane mirror. A plane mirror. Observe the image of Paul taking meat from the pot. Observe the image of Paul taking meat from the pot. Observe the image of Paul. Observe the image of Paul. 1 centimeter to her. Taking meat from the pot. 1 centimeter to her, taking meat from the pot. What is the total distance? What is the total distance of Paul's to Ashiat's image? What is the total distance of Paul to Ashiat's image? That's number 4. Number 5. So that we go to curved mirrors.
Wake up now, wake up now.
Number 5. A mirror is placed at 60 degrees to another. What is the number of images? What is the number of images formed in the mirror? Number 6. Number 6. True or false? all romantic one, all the rays falling on mirror, all the rays of light falling on mirror is totally reflected. All the rays of light falling on mirror is totally reflected. Two. Lunar eclipse happens when the moon is between the sun and the earth. 3. Lunar eclipse occurs when the sun is between the earth, when the moon is between the sun and the earth. 3. Annular eclipse. Annular eclipse occurs when moon is closer to the earth. Annular eclipse occurs when moon is closer to the earth. That's 3. 4. I'm not saying anything.
I've answered it. Yeah.
What you have said is technically correct, but the question is still.
Yeah, still talking. Cannot be one of them. None of their work.
Can someone be taking meat?
The answer is
So if you are observing someone in this
What's his name? Someone.
So 4. I hope you are following. A mirror rotated at angle of 30 degrees as its reflected ray rotated through 60 degrees. Through 60 degrees. If the incident angle is altered. So let me repeat the questions again because of those online. Number one says that a ray of light strikes a mirror at 30 degrees. Determine the glancing angle, reflected angle, and the deviation. Number 2, the following are attributes of plane mirror. The following, the following attributes of, you will not be reasoning with someone in the exam. The following are attributes of plane mirror, except A, U equals to V, B, image is inverted, C, magnification is 1, D, HI is equal to H naught, E, none of the above. Number 3, JP stands in front of the plane mirror at a distance of 10 centimeters to the mirror. If his image height is 200 centimeters, determine its magnification in the mirror. Number 4. Aisha standing at a distance of 2 centimeters to a plane mirror. Aisha, there is no I in Aisha standing at a distance of 2 centimeters to a plane mirror. Observe the image of 1 centimeter to her, taking 1 centimeter to her, taking meat from the pot. What is the total distance of pulse to Aisha's image? That means pulse, and this is a pulse image of pulse to Aisha's image. Then, number 5. A mirror is placed at 60 degrees to another mirror. What is the number of images formed in the mirror? A mirror is placed at 60 degrees to another mirror. What is the number of images formed in the mirror? Number 6. Answer true or false. All the rays of light falling on mirror is totally reflected. All the rays of light falling on the mirror is totally reflected. Roman figure 2. Lunar eclipse happens when the moon is between the sun and the earth. Lunar eclipse happens when the moon is between the sun and the earth. Roman figure 3. Annular eclipse occurs when moon is closer to the earth. Roman figure 4. A mirror rotated at angle of 30 degrees has its reflected rays rotated through 60 degrees if the incidence angle is altered. Full stop. So that's all about the questions. So leave your answer in the comment section quickly, and let's see who got it right and who did not get it right. Are we there? Sir. Is anybody saying sir? Are you true? We want to quickly move on to curved mirrors, and we are ending by 1. This is 12:45. But we have to do curved mirror. So let's just say 1 to 1. It's not much. If you have understood what you have been saying, curved mirror is not much. So we know that refraction and lenses will be our next class. I have exam on Monday and my final paper is on Wednesday. So as from that Wednesday till the exam, gather day. So can we move on? So if you are writing SES JAM and you have joined the class, it's a very big congratulations to you. Just work hard. Work extremely hard, because all of these things now we will still do them again during JAM classes. But now if you have known them now, explaining them again, sometimes you get better time over time. So don't be scared, but make sure you give it all your best as if you are also writing the exam tomorrow. And SSC is getting tougher now. Normal school now, they said that it's going to be online. So the stage is coming that all this writing on the board for you will be stopped. That people will be helping you in the exam form to stop. So all of you can now face your exam properly. Because I don't know what's wrong with students. We will take time and teach. And sometimes some students will still go and be cheating in the exam. But the advent of writing your computer exam will not allow that again. How many people can cheat in JAM now? By the time you start writing WAEC online, that you sit down like this and they pop up your question. Theory, only your own question, 1 to 15. Another person, different questions. And you understand what life is all about. So it will make Nigeria get better, and it will make our education get better. Because everybody will have to read. Not people just go to school just by pushing them. So we pray that our technology gets there so that things get better. Before now, they used to help in jam. People will sit for jam, but these days now, that has been cut to the bare minimum. And even though those people cheat in jam are still arresting them because things have changed. So are you true? I just want to see, because there are some things I digged into those questions that might confuse some of you. So number one, you can solve number one, Abi. You should all leave your answer. But let me just hear a chorus answer. What's the answer to the G? 30. If you did not get 30 for G, that means for to she questioned for me. Nika, you have missed it again. What's the answer to R? 60. And your R will be equal to I, Abi. So if you want to calculate D, that means your D will be what? Yeah? D? 60 times 2.
120.
So 180 minus 120. So your D will be 60. 30 times 2 will also be 60. Is that taking? Oh yeah, the next one. Number 2. Now what the options are, the right answers are they dropping answers in the comment section? Okay. Number 2. Which one is correct? None of the above, I think which one is correct? None of the above. G is 30. Strike the mirror at 30 degrees. That means that the mirror, the angle to the mirror is 30. The incidence is 60. The mirror, it strikes the mirror at 30 degrees. So it's the mirror. As he's striking, I know you what you want to hear. Maybe it makes the angle with the number of the mirror. But since he's striking the mirror, so the mirror has an interface. So the angle it makes with the mirror is 30 degrees. That's how you take it. The answer to number 2. Which one? B or D? B. If you have said that the answer is, did you say D? B. None of the above. None of the above is actually correct. So those of you that said none of the above, because it said except, and everything is correct, except that this guy is actually wrong. Your answer is B. Answer is B. Image is inverted. What does inverted mean? Image for a plane mirror is laterally inverted. Lateral. It does not flip. It will just change its side. Do you get that? So if I say lateral inversion, what I'm saying is that if I just say inverted, listen. If I just say inverted, that means I'm saying that it went upside down. Sure you get, but that's not what we have. It has to be lateral inversion. That's why I said it that way, because I know some people. So the answer is B. Is that taken? Yes. JP stands in front of the plane mirror. So what did you calculate? What's the answer? 1. So you don't need to calculate anything. Is that taken? So for this question, you don't need to calculate anything. They said that you people are doing 1 over FM equals to. You see, that's how UI concept sets exam for you. That's why most of these schools that want to test your knowledge, they set exam. They are not doing 1 over F is equal to 1 over M is equal to 2 over Q. The moment you saw this plane mirror, Magnification in a plane mirror is what? The answer is just 1. You don't need to solve anything. You are growing, It's little by little. So JP stands in front of a plane mirror at a distance of this to the mirror. If its image height is 1, do you think you can even solve this? Is the information complete? It's just to waste your time. It's just to waste your time. 200 centimeters determines magnification in the mirror. The moment you say plane mirror and you say magnification for a plane mirror is always 1. And if you look at it, if the subject, if he's standing in front of the plane mirror and the distance is 10 centimeters, even if you want to calculate, what would be his object, the image distance? A magnification of the image distance to object distance, would that not be 10 over 10? That will give you 1. Do you get what we are saying? Understanding matters a lot. Do you understand that? Even if I say his height is 200 centimeters, what would be his object height? What would be his image height? So, you don't need to calculate it. A shared standing at a distance of 2 centimeters to a plane mirror. So, in this case now, she's standing in front of a plane mirror, and her distance to the mirror Stop. She made here and she's covering her hair. So she's looking at herself in the mirror, and her distance to the mirror is 2 centimeters. So she observed the image of Paul 1 centimeter to her. Now, someone asked me a question that the 1 centimeter is in front of her or at her back. Technically, it will be at her back because she is observing it in a mirror. Do you get that? So it can't be at her front observing it in a mirror. It's possible. We are not saying it's not possible, but technically, if you observe something in a mirror, that means that thing was not actually direct in front of you. Do you get that? So, you know, all these questions are coming often, so it's not like maybe I'm copying them from somewhere, but I need you to understand what we are dealing with. So, observe the image of Paul 1 centimeter to her, taking a knee. So, she observed the image. You know, there are different ways in which you could have interpreted that actually, either from the mirror, but do you think that if she observed it 1 centimeter to her, if it's in the mirror, do you think that's possible? So if I say 1 centimeter to her, you know it could have actually been from the mirror. But do you think that is possible? So technically, that's also not possible. So the only place you can be 1 centimeter to her is at her back. Do you understand that? I did not now say 1 centimeter to the mirror. I said 1 centimeter to her. So now, what is the next thing? What is the total distance of pulse to Aishat? If I say pulse, I did not really say pulse image. Is that taken? That means where Paul is to Aishat's image. So now, this is Paul. Where do you think Aishat's image will be? To the mirror, what will be Aishat's image? So she will be standing also 2 centimeters. That's her image. This is the object. Do you get that? So what will now be this guy's distance to her image? That will be 1 plus 2 plus 2. Do you understand that? Where is Paul? There's 1 centimeter to her. Her own distance is 2 centimeters. And her image is 2 centimeters. Then we now say what's the total distance of pulse to? So from Paul now to Aishat's image. It's supposed to be yes. Yes. Because if I say pause to Ashiat's, that means I'm saying that pause image to an Ashiat's image. Because I'm made it processing. Is that taking? So pause image to Ashiat's image is going to be 1 centimeter. It's just going to be because pause image will be at her back. So from map, it will still be 1 centimeter. But if I say from the mirror, pause, if I say what is pause image distance from the mirror, then pause image distance will actually be 3 centimeters. Do you get that? That means that pause will be from the mirror now. 2 plus 1. Please, do you understand what we are saying? It's just that for you to just think about it, we are just using the properties of mirror to create. So, what's the answer to this? 5 Abi, that's 360 divided by 60 minus 1. Do we understand that? How about this? True or false? Roman figure 1. True or false? True or false? False. All the rays of light falling on mirror is totally reflected. True or false? False. It's false. Part of it is even refracted. Because it now depends on thickness. You know, if I look at a plane, if I look at a glass and the glass is plain, depending on the thickness, if I look at it, the ray of light will pass through, I can't see myself. But by the time I paint the back, what is making me see my image is due to reflection from that back. So if the light hits the glass, it will still enter the glass a bit before it is now sent back by the painted wall. So it will still refract. People that have done refraction will understand that. If you have not done refraction, you will learn it in the next class. But when light falls on something, it is either reflected, refracted, absorbed, or it is transmitted. Abi? So it is not everything that will be reflected. That thing that you are saying that green lights, green leaf reflects light from the sun. When the light strikes the green leaf, it will send back some parts and it will absorb some parts. Abi? It will send parts, a part that it has the same wavelength with, and that's what you will see. So this statement is false. Linear eclipse, lunar eclipse occurs when the moon is between the sun and the earth. True or false? False. False. I said lunar is what? You said. So that's false. Abi gave to Tushima. Annular eclipse occurs when moon is closer to the earth. True or false? False. False. There's only few people that are answering you. True or false? That's false. You know that when the moon is closer to the earth, I did it. That's why, because someone asked that question online, that when will it happen? You know, this is the sun. If the moon is close to the earth, the rays coming from the sun cannot intercept. Abi? But if the moon is close to the sun, then when the ray passes, they will definitely intercept. Do you get that? Because of, so the moon, if the moon is closer to the earth, you can't have an annular eclipse. It only happens when something is at micro-G and those terms. Is that taken? So now, the next one. So Roman figure 3 is false. Roman figure 4, true or false? False. False. Why is it false? So if the mirror is rotated at angle theta, the mirror, the reflected ray will also rotate through 2 theta. Only when the incidence angle is kept constant. Is that taken? But the statement said that when the incident sample is altered, and that's already made it false. Do you understand that? The answer is correct if this statement did not end it. It would have been true. It is that last statement that made it false. Do you understand that? Okay. So that's that. So can we move on to curved mirror now? Curved mirror is the technical part. These ones are straightforward. The technical part is curved mirror, but it's not that difficult. Is that taken? The major thing that makes it technical is just interpretation of questions, which is still the same thing as what we have been doing. Please, if you are writing UI does not set more than all of these things. You just need to be wise in dealing with UI questions. So, we still talk about everything. What way you said, you just want it to look like you have never had it before. But there are things you have had. Even in the chemistry, there are some things in your background that they will just ask. But it's only the chemistry. But even if you are a secondary school student and you are writing with the for the first time, and you are very good in your secondary school normally, then you will still do well in physics. I can't promise you someone of biology. I can promise you for physics and the aptitude you have to be. But for the chemistry, nobody teaches you, you have no idea. You can't score more than 20. So that's the chemistry. But the moment you know it, you can score your 10. That's the way. So it's not about valuing your secondary school. You can only score maybe like 3 based on knowledge. But if you want to score your 10, you need a class, a serious class, a serious reading, a serious research. Biology you can still score 7. You can even still score 9, even if you have no idea of what do you use to set. Sometimes you just chip in like 2 questions. That will be very strange. A question like what is the botanical name for giraffe? Just chip it in. Just chip in like all these obligates, facultative, they are still normal. You can just chip it in like all these are notes, they are notes of it. So we will look at them. What is the percentage of light absorbed transmitted? How many jambas to think about that? What is the difference between acrodonts, fluorodonts? They are not your normal level textbooks. So that's just what makes the difference. But the moment you are used to all of them, we also do it. And another thing is trying to technically ask you what you know. Not giving you the direct name, but just trying to ask you what you know them. So, so for curved mirrors, so this is 124 by 130. We'll try and stop it. Either we finish it or not. But it's not something much. If you can open your brain, it's not much. It's what we can finish in 30 minutes. But if you are finding it hard, so let's quickly do it. So for curved mirrors, the first thing is that you need to know the formation. I already drew it for you the other time. Knowing the formation will help you to understand a lot of things about it. Let's say you have a spherical glass or something, and you cut a part of the glass. You have a glass like that, and you cut a part of the glass. Then, let's say this is the part you cut. Then you decide to paint the outside. That's what will make you understand some terms, so that's why I'm trying to start from there. If you decide to paint the back of the glass, then you can use the inside to see. That'll be just like a spoon. You can use the inside to see. That inside gives us a type of mirror. And what did we call that? I told you that when it is inside, you know cave. Cave means inside. Concave. Concave is also known as converging mirror. And why we call it converging mirror, you will see with time. But just note this, it is called converging mirror. If you decide that you don't want to paint the outside, it is the outside you want to be using to see, like the ones you have in majorly cars. Then, if you paint the inside and you see from outside, then we call it a convex mirror. Convex is the one that used to do like this. That's why if you see lens too, this will be convex lens. The one that used to bulge out, or the one that used to be like an inside is your cave. Do you get that? We'll come back to this later. So, this convex lens is also known as diverging lens. Diverging mirror. So, convex mirror is known as diverging mirror. You can see where I'm coming from. Please follow so that you will understand it. Now that I have the mirrors, I have my concave and I have my convex mirror. Then I need to talk about them. Then to talk about them, I need some terms. What are those terms? First is something called aperture. Aperture is just talking about the width of the mirror. So if you cut it, it's not the same thing you will cut from something like this. Abby, there will be a longer one here, but there will be a smaller one here. That's just like the aperture. The next thing is the center of that mirror. What is it called? You know, I cut it from here. So if you divide it into two, the center of it, that is called pole. I hope you're listening. It's not so hard. It's not so hard. The center of it is called pole. Then everything about physics sometimes we just be imaginary. I can run a line. So using concave as an example now. If I have the center, then I have a line. Don't mind the line. It's not there, but let's just imagine it is there. So that imaginary line that runs through the center of the mirror, we call it principal axis. I hope you are following. So it's an imaginary line. Where did it pass through? The center. Where did I call the center? The pole. Abby, what did I call this line? Oh yeah, are you following? So that I will not waste time here. What did I call this imaginary line? Principal axis. The center of the mirror is called what? Pole. I hope you are following. We have another one called center of curvature. Center of curvature. Now, listen to this. What do we mean by center of curvature? Where did I bring this mirror out from? From this sphere. Abby, where did I curve it out from? I curved it from a sphere. What is the center of that sphere? That is what we call center of curvature. It is that center of the sphere from which the mirror forms a part. That's center of curvature. The center of the sphere from which the mirror forms a part. Do you get that? Now, if I take this part away now, it's part of this sphere. If I remove it like that now, so it's part of the sphere. So this mirror is the complete part of this thing. So the center of that place now, from which the mirror forms a part, then is what we call center of curvature. Do you get that? So that is your C. So that C on a mirror is usually represented at a particular position. So you always put it like that. The next one you have is what we call principal focus. So this is a term, principal focus. This, what type of mirror is this one? Concave. So now, I want to put the two together. This one is what? Convex, Abi. So it has its principal axis, it has its pole, Abi, and it has its, since I'm looking from here, so let's put, it has the center of curvature. You know, I'll be looking at the mirror from here, Abi. So, let's move on. Now, are you following? This principal focus is a point on the principal axis where all the rays that are parallel to the principal axis converge or appears to converge. It's a point where all the rays that are parallel to the principal axis converge or appears to converge. Is that taken? Well, let's see what I mean by that. Let me start with my image. You know, I'm looking at this mirror. So let's say I'm standing somewhere here and I draw a ray of light from my head. If I make the ray of light straight, you know, this ray of light and the principal axis, the both of them are parallel, Abi. So that's why we said any ray that is parallel to the principal axis, when it strikes the mirror, it will reflect, you know, law of reflection, Abi. That point where it will go is called the principal focus. If another ray comes like this and it reflects, that's where it will go. I hope you're following. If another ray goes parallel like this, that's where it will go. If another ray goes parallel, anytime it's sharp parallel, that's where it will go. And that is the difference between this concave mirror and parabolic mirror. This thing that we say that it will always converge at this point is not true in total for concave mirror, but it's true for parabolic mirror. All the rays always converge at the common point for parabolic mirror because of the curve. This one is not totally curved like that. So most times the ray don't meet at that exact point. That's the error. And that's what parabolic mirror is there to correct. But let's move on. We still get that, we repeat that again under the application. So now, what did I call the principal focus? It is the points where all the rays that are parallel to the principal axis converge or appears to converge. Let's see the word appears to converge. You know, I'll be looking from here now, if it's this one. If I draw a ray that is parallel to the principal axis, for this mirror, they always diverge. Take this place as if it's like this. If you have something that is like this and a ray is coming straight like this, how do you think it will go for the reflection? Abi? So take a mirror that is like this, so you see the difference. I take that small part. If a ray is coming like this, how will they go? To come down. Can you see the difference? So for this one, when the ray is coming, they usually diverge. That's why we call it a diverging mirror. But for this one, when the rays are coming, they usually what? Converge. So now if you trace this incidence ray with the reflected ray and you trace them back, you will realize that they will appear. So if someone is looking at the mirror, the person will see them as if these guys are actually coming from a particular point. So that's why we said appears to. So in my definition, I said where the rays converge and where the rays appears to converge. That's the difference. So now looking at this, you can see that the ray that is coming here now, they did not meet, Abi. But the ray that is coming here, they eventually meet at a point. That's why we call real. This one is what we call virtual, because there is not the rays that meet. So now, that point is still the what? The principal focus. So now, you need to now know something. Please, do we understand what principal focus is now? Any ray that is parallel to the principal axis, where do they always meet? At the principal focus. Is that taken? So that point is called the principal focus. The point is called what? Number 6, there is what we call focal length. Small f. Focal length. The unit of focal length is centimeter. So if I already have principal focus and I have my pole, the distance from that principal focus to the pole is called what? Focal length. Is that taken? The distance from principal focus to the pole. Just take from here to here, that's your focal length. From here to here, that's your focal length. So you need to now note something here. Please, do you understand that? You need to know something here. Your focal length for concave mirror is usually positive. Why? Because it is real. Abi? So when you are solving questions, your brain has to think about that. Especially when you see converging or diverging or something. Why are you sitting on the floor? The floor is dirty. Stand up. So this place now, the focal length is going to be what? Negative. Do you understand that? So now, the next thing to add is what we call radius of curvature. Radius of curvature. We represent that with small r. So, radius of curvature is, you remember, if you look at this, the center of a circle, please listen, you know the center of a circle, the distance from that center is called radius, Abi. So if I now say this place is the curvature, if I say that's the center of curvature, so the distance from that center to the pole is going to be called the radius of curvature. Do we get that? You know this is the sphere now. If I have a circle and this is the circumference of the circle, this is the center of the circle. Distance from the center of the circle is called what? To the circumference. That's the radius. Abi? So if I have a sphere from which I form the mirror and this center is my center of curvature, the distance from that center to the pole, you know the center of this guy is pole. So the distance from there to there will now be called what? Radius of curvature. Do you get that? So the distance from C to P is your radius of curvature. The distance of F to P is your focal length. So now note something. Hey, stand up, Joe. Why is this bet? I'll beat you now. So this is negative and this is positive. Now, for radius of curvature, it is the distance from C to P. Shall you get? But from F to P is your F, normal focal length. So note something here. Your focal length is R over 2, or just say that R is equal to 2 times the focal length. That's the normal thing. You can derive it. All those formulas. Your radius of curvature is usually 2 times the focal length. So don't mind the fact that this one is looking a bit longer than this. It's because I'm drawing and I'm explaining. So if you have a mirror, it's something you need to have at the back of your mind. If you have a mirror and you draw your principal axis, and this is the pole, and this is your focal length, your focus. You know the distance from here to here will be your focal length, and this is your C. Don't forget that the distance from C to P is twice the distance from this to this. So if I say from here to here is 10, that means from here to here will be what? 20. you get that? Because there are some questions that they won't tell you all of these things. It is from the question you will know, and you have to let your mind follow. So that's one relationship. So these are the things you need to know. These are the terms we use to qualify these guys. Now, if I'm not looking at myself in this mirror, what do I see? I'm looking at myself in a concave mirror, what do I see? I'm looking at myself in a convex mirror, what do I see? So that's what we want to talk about. So images from... I have 10 minutes now. So images formed in a I will do one for you. You can go and do the rest yourself. As assignment. Images formed in a curved mirror. Images formed in curved mirrors. So what we are going to do is that we have rules that we follow in drawing images in the curved mirrors. The first rule is what you need to follow all through. Let's see. So we have two of the rules that we are going to pick. Let's say this is the mirror. If you want to form the image of this object, the first rule is that you can take your ray from the top, from the highest point. Now, draw a parallel line to the mirror. We said any ray that runs parallel with the principal axis, where does it go to? To the principal focus. Abi? So it will meet at the focus. So just draw that one. That's rule 1. So when you pick that one from here and you go parallel, it will go through the focus. Rule 2. We are going to use this rule in drawing all our images. Any ray, let's say this is the object, and this is my F. If you want to take it this way, any ray that goes through F, when it strikes the mirror, it will go parallel to the principal axis. Any ray that goes parallel to the principal axis, when it strikes the mirror, it will go through F. Any ray that goes through F, when it strikes the mirror, it will go parallel. That's another rule. Rule 3. Rule 3. Taking it from the same head. Any ray that strikes the pole at this angle will be reflected through the same angle. So we say that any ray that strikes this obliquely will be reflected obliquely. This angle will be the same as this angle. That's just so if the ray strikes it at the pole, it will be reflected through the same angle. That's rule 3. You just need 2 of the rules to draw your images. Rule 4. This is our principal focus. This is our center of curvature. If I draw my object, any ray that goes straight like this and passes through the center of curvature will be reflected back. Any ray that is coming from the center of curvature will be when it strikes the mirror, it will also go back through the center of curvature. So it's straight. That one does not work. So that's that. So those are the 4 rules we are going to use to draw the images. How many minutes more? I have 6 minutes more. So now, let's look at it. For these rules now, we now want to put objects at different positions. What will be the image and what will be the characteristics of the image. So first thing I want to do is for concave mirror. So I'll just do one simple one. This is what we want to do. This is a concave mirror beyond C. So I will take the first rule. That one says that if I go parallel, after reflection, where will it go? Through F. If you are drawing it to That's for our extra, you can use it. But the moment you do everything off and you don't need to stress reflection. So it will go through F. This one says that if it pass through C, now we have to extend it, so don't let me use that one. So if I pass through this one now, I went parallel and it was reflected. So if I pass through F, it will go back like this. Abi, it will go parallel. So if the distance goes like this, then it will come back like this. What did we notice? They intersect at a point. Abi. So now at that point of intersection, that is where the image will be formed. So you will now, you are starting from the edge, so the head will be here, so you can just draw the rest. So what you will now say is that, what are the characteristics of the image? Where is the image formed? So when we place the object beyond C, the image is formed between what? C and F. What are the characteristics of the image? It is inverted. That means what is Dorikodo. It is what again? Is it real or virtual? You can see that it's the same rays that are coming that actually meet. That's what we mean by real. So it is real. And it is what? It looks smaller in size than what it was coming from. So it is diminished. If it is diminished, the magnification, will it be equal to 1, greater than 1, or less than 1? So the magnification will be less than 1, and that's it. So you can try the rest. We'll continue from there. So we'll continue from there in the next class. So
This is it.
It's more easy.
I don't know when the next class will be, but maybe on Wednesday. We could have had it tomorrow.
Mariam.
So we'll complete this in the next class, and I'll give you questions on everything. When is our next class? I don't know. So it's most likely definitely going to be from Wednesday. Either Wednesday or Thursday. If my exam is in the morning on Wednesday, I'll still have it on Wednesday. If my exam is in the afternoon, then we have it on Thursday. Oh, Thursday.
Location.
So we have our class on Thursday, next week Thursday, there will be no class, there's fasting and prayer.
Where's
So
the
don't come
location?
to at all.
We are going to location.
So you guys should take it. Go and practice questions on all those parts you have solved. So if you are online, you can subscribe. So you can subscribe to the channel, so when we start another class, you get an update on the class and all the necessary information. Okay. God bless you. I'll see you next episode.